questions about the homework at all? What's that? Which one? What is it? You have a question? Yeah. Yeah.
I have a real quick thing. It's about just the properties for the DTF2 transforms. For sines of omega naught and times x of n.
All right, let me do it this way. Let's say we have x of n, and we know it goes to x of omega. Let's assume that, all right? Now, if we have x of n times the sine of omega naught n, that's capital omega naught n. That's just like the sine transform that you have with Fourier transform. It's just going to be a regular Fourier, continuous time Fourier. J over 2 times the quantity x of omega plus omega naught, and this is going to be minus x omega minus omega naught.
The main reason I ask is because on page 398, the whole thing, it's listing it as what should be like 1 over 2j, and then x of omega minus
You
omega.
sure it's not just sine of omega?
Oh, yeah, that is, because I
It's
was,
just sine of omega. Look, I'll even show you how it works. We know that works. Y'all, are you okay with that? That is the basic modulation property, that and the cosine. All right, now, fine. I can't prove this now, but do y'all remember continuous time Fourier transforms? Do y'all remember if you had 1, it went to 2 pi times delta of omega? Do y'all remember that? How many do? Give me a show of hands. I proved that using duality. You're going to see you're going to be able to use a lot of Fourier transform reciprocity properties here for the DTF2. You're going to like it. Now that's true. I want to tell you one other thing. This is true as well. We've got to do one thing. We're going to put a 2 pi, and we're going to put omega down here, but we're going to subtract or add 2 pi k, and then we have to put a summation here for k equals minus infinity to infinity, because remember it repeats itself every 2 pi. So that's why I put the 2 pi k and put the sum going from minus infinity to infinity. Are you with me? Now what he said is something interesting. He said, and here's what I'm going to do when I do this. I'm going to ignore all of these that are outside the original minus pi to pi, and I'm going to say, what I'm going to say is this. 1 for me is just going to go to 2 pi delta of omega, and we know it repeats. Do y'all agree with that? We know it's going to repeat every 2 pi. It just keeps stepping, repeating up and down the omega, capital omega axis. So now when I go here, since I have my x of n, literally, I'm going to say is 1, and therefore that goes as 2 pi times delta of omega. I think this is your question. Now when I stick that in here, well, this is my x of omega. So when I put the sine, just the sine of omega naught in here, that goes, still is j over 2. But now I have 2 pi delta of omega or plus omega naught minus 2 pi delta of omega minus omega naught. Y'all see this, class? And that's what he has, I think. But he's going to make this step and repeat with, he'll have the minus 2 pi k minus, yes.
the main thing is when it shows that it goes transform and has the,
What's that? Say that again?
it shows that out front instead of it.
Well, here's what he
resolving
does.
to
Let me just show you. He gets rid of the 2's, right? So you get rid of that 2 and that 2, and then he'll put the pi out front. So we'll have j pi or pi j or something like that.
And the book it has, oh, yeah.
And that's what he does. Follow me? I hope you all see. Well, hold on. Do you see this?
Yeah, it just had pi over j, and I forgot that goes to negative j.
All right. If you
Yeah,
want to
yeah.
put a 1 over j, then you reverse these.
Yeah,
I'm sorry.
just realized.
But, you know,
that.
that's-
Thank you.
I do it that way. I always put a plus j
Yeah.
out front. That's me personally. Go ahead.
What's this? It's X.
But before I continue, do you all see what I did here with that property? You all understand what I've done? It's simple, what, don't you understand, when you shake your head like that makes me nervous, what?
I mean, can you further explain it like this, step by step?
All right, I'll do my best here. You agree that 1 goes to this, right?
Yes.
All right, now, we don't put the 2 pi, I'm not putting the 2 pi k in that argument and put a summation because it'll get too cluttered. Do y'all see that? I'm only focused from minus pi to pi. I know here I should put a 2 pi k, plus or minus 2 pi k in each of those arguments and have a summation. Are you clear with that? So I'm ignoring that because I don't really care about that. I care between minus pi and pi. So if this is this x of omega, right? Well, replace omega with omega plus omega naught. What is it going to be? It's going to be delta of omega plus omega naught, and that's delta of omega minus omega naught. The constant 2 pi I bring out in front, and there was a 1/2 there, so I'm left with pi j. That's it. All right? Y'all see this? This is not hard to see. It's very obvious if you just think about it rationally. Are you clear with this? Now, it assumes we know the transform. The trick with this one is the coefficient of this is 1. Therefore, 1 goes to that. That's the trick. If you want to say there's a trick. All right. Did you have another question before I'm done with you? All right. Kenny?
Can you do, it's like parentheses 0.5 to the.
Oh, good, good, good. I didn't get to that. If you did the reading in the book, you picked up on it. They want a DTFT for, and now it's going to be a defined series over finite values. Now, here's what they do. What problem is this, by the way?
This is G on 4.
What's that?
G on 4.4.
And it's 4.4G. So they give you a defined value. They say X, and there's a bracket here, isn't it? It's either going to be curly brackets or square brackets. Are these square or curly?
Neither, it's a parentheses.
This?
Yeah.
It should be a curly bracket. Wait a second. If we're doing G, it should be this, right? All right, don't worry about it. Give me the values.
0.5 to the absolute value of
I
n.
thought this was fine. I'm sorry. What is it?
0.5 to the absolute value of n times cosine 4n.
What?
4n?
All right. And they want to transform that, right?
Yeah.
Now, several ways to do this. I'm going to tell you there's so many ways. Let's just look at this one. 0.5 absolute value of n, right? Think about this. Isn't that equal to, right here, isn't that x equal to really, I'm just going to do it this way. Let me do it this way. I'm not going to call that x. I'm going to call this function y. Y of n. And I'm going to say that now my x of n is equal to 1/2 absolute value of n. That's what I'm calling it. Now what's another way to express this? Follow me on this. Isn't this expressible in terms of 1/2 to the n, u of n? Remember, that series starts at 0, doesn't it? Plus what? Plus, now what are we going to put here? We're going to put 1/2 of minus n, follow me? And I want it for n that are negative, right? So now what do I do here? I put u of, not minus n. Minus n would do what? It would take us from minus infinity to 0, right? Do we want 0? So what do? Plus 1. Follow me? Think about it. If I do minus n plus 1, I'll show you what I'm talking about. Or minus 1, pardon me, minus 1. Now watch. When n is 0, or say when n is 0, that's minus 1. Do you follow me? U of minus 1 is 0, right? Agreed? Follow me? When n is 1, I have minus 1 plus minus 1, or minus 2. U of minus 2 is 0, right? Now bring it back when n is minus 1. Minus of minus 1 is 1. 1 minus 1 is 1. Do you all agree with me? 1 minus 1 is 0. 1 minus 1 is 0, and this becomes 1. Now, I'm thinking ahead. I gotta stop. Are you clear with this? In other words, it's gonna count from, it will always be 1 from minus infinity, n equals minus infinity, to n equals minus 1. But at 0, it is, at 0, n equals 0, it is 0. Do you see that? And doesn't this represent this series? For all values of n. How many see this? You're looking at me, I don't believe you. Do you all see it here? Just put in numbers. Pick a number. If it's the absolute value of n, if n is 0, it should be 1, correct? 1/2 to the 0 is 1, is it? Well, when n is 0, this one turns on, this one is 0. It is 1, right? What about n3? When n is 3, minus 3 minus 1 is minus 4. You have minus anything is 0, correct? That's gone. You have 4, right, or n equals 3. It's on, it's 1/2 to the 3. It works. Do y'all see this? Give me a show of hands if you do. All right, now can I take the transform of these? What's this one right here? I hope this answers your question. Anyone? Come on. Got to know this for the quiz. Well, there A is 1/2. Let me give you a clue, right? A is 1/2 in the properties, and so this is what? I can put it as 1 over 1 minus 1/2 e to the minus j omega. Anti-class? Y'all agree with that? What about this one? Ah, that's a tricky one. How do you get this one? I'm going to do this one. I'm going to do you a favor. I'm actually going to show you this one. This is a trickier one. You can use a property, you're right, because what do you know? U of or x of minus n is x of minus omega. Do you remember that? Look at the property. We could do that. I want to show you. I'm going to do this for you. Now, let's just get, we're going to brute force this one. We're going to go ahead and get the actual transform of this. Brute force. I'm going to say x of omega is defined as the summation, technically, n equals minus infinity to infinity of my x of n, 1/2 to the minus n, times u of minus n minus 1, times e to the minus j times n omega. I'm going to put in there just so you all see this. Y'all agree with that? People? I literally use the brute force way. I'm going to take the fundamental definition and I'm going to evaluate it. And I know I can do this fairly quickly. Now, what are we going to do on this to make life easy? Where is this going to be 1? From n equals minus infinity to minus 1. Correct, class? You all see that? So now I can change my limits from minus infinity, just leave that there, to minus 1. Right? And get rid of this. You all agree with that? Agree? Now, there's several ways to do this. I'm going to do it the way I think would make the most sense to you. Now what I'm going to say is, I'm going to combine these exponentials, or get a single exponential, so I have it's the sum from n equals minus infinity to minus 1 of, now it's going to be 1/2, right, times e to the j omega, right? And this is going to be minus n. Do you agree with me? Agreed? Now, does anybody know why I left that minus n there? Why? Yeah.
You're going to flip your balance.
I sure am. Now I'm going to do this. Rotten person that I am. Instead of counting from minus infinity to minus 1, I'm going to count from infinity to 1 and make that a plus. Got it? So now I can change them. I can go from 1 to infinity and make this a plus. Isn't that exactly the same thing? And now what happens? Well, I told you before, this is now like my hypothetical a, right? And we had a to the n, and we counted from Q1 to Q2, you got what? It's going to be 1 minus 1/2 times e to the j omega downstairs, that's 1 minus a. Upstairs, it's going to be this, evaluated at what? The lower limit, right? Which is just what? 1/2 times e to the j omega, correct? And it's going to be minus this evaluated at infinity, correct? What is 1/2 times e to the j omega to the infinity power. 0, because 1/2 to the infinity is 0. Is it not, class? So you don't need to put that in there. And that's what this one is. Y'all see that? Yes, sir?
Why do you go from the lower limit to the upper limit?
Doesn't matter. When you sum, you can go this way from 1 to infinity or infinity to 1. Doesn't matter which way you count it. So I just swapped it because that way I get the 1 on the bottom. I'm used to seeing it that way. Y'all agree with me? How many see this right here? Now, she's looking really concerned like I've done something wrong. It's exactly the same as the other one, except notice that that now is a plus, not a minus j omega, and it has this because now our count starts at 1, not at 0. That's the only difference, understand? So now we got this one down here. This is where I'm going with this. Now I put this one, 1/2 e to the j omega over 1 minus 1/2 e to the plus j omega. I'm not going to do this here, but I'm going to tell you right now, you can get a common denominator, and when you do so, this thing will reduce itself to a very simple form of a, I believe it's a sine type form, but leave it like this for now, understand? Because these are exactly right, those two. Do you understand that? You all see it? And what is this? This is my x of omega, correct? Now, I've got it multiplied by this cosine garbage here, this cosine of 4n, right? Omega naught is 4. Do you all see that? The coefficient of n inside the cosine argument is 4. Omega naught is 4. So you simply do this. You take this functional form right here. You replace omega with omega plus 4, everywhere omega exists, and then do it again in omega minus 4. And then you put it into the form that I had up here a second ago where it's j over 2, bang, now j over 2, 1/2 times the x of omega plus omega naught, then you add to it x of omega minus omega naught. Do you see this, Kenya? You see how I did that? Now I did one thing, the book may have, I could use a property, I prefer to brute force it. I just did this brute force. The book, does it have this one in there? Does it have the transform for this right here? 1/2 to the minus n, u minus n minus 1. It does have that one? And it should be of that form, is it?
Yes.
All right, there we go. Good? What else you got for me? You've been giving me dirty looks all day. You have one for me? I don't blame you. I had one prof I used to, he's a genius, and he could see 5 steps ahead of us, obviously this one. How?
You do number 1.
Yeah, I think.
Question about the 1/2 to the end here.
Go ahead.
Would that just be e to the j omega over e to j omega minus 1?
All right, what he's saying is this. Now listen. Don't pay attention to this one. Get rid of that. If you just have this, all right? Just this. Multiply top and bottom by e to the j omega. Just do it in your mind. Top would have e to the j omega, right? This would become e to the j omega. And this would get rid of that e to the minus j omega. That's exactly you can have that form. That form comes in, it's useful. You're going to see it later on, you filter. It's useful for things, but either form is correct. You understand that, class? All right. Now, what did you say? Tell me what it is.
X in brackets equals 1. From 0
n equal
equals 1. From 0 to 5 inclusive.
less than 5?
Mhm.
Less than or equal to 5?
Yeah.
What is that, people? One word. Pulse, isn't it? Isn't that a pulse shifted? Where's the pulse centered?
2.5.
It's 1 from 0 to 5. There are 6 values, right?
3.
It's centered at 3, correct? Follow me on this. Here's 0, 1, 2, 3, 4, 5, 6, right? Now look, this is where it's 1. I wanna make sure you see this, because people mess this one up. And by the way, there are no dumb questions, unless it's about football. This is the function that they want. Now, you could put a u of n minus a u of n minus 7, all right, if you want. You all see that? That would represent it. It's easier with a pulse or the rep, and I like the pulse. So this, if this is my x of n, I would represent s as a pulse. What's the width of the pulse? 6, right? There are 6 ones, right? So it'd be 6, or like I put it, it's 2 times quantity 3 here. That reminds me I have 3 on either side of the center point. Understand, class? Now, I mean, there's actually 7 values, sorry, 7 values, but they have what? A span of 6. Do you all see that?
Could you explain why x of 6 is 1 and not 0? From the definition?
I'm sorry. I'm sorry. I'm sorry about that. He says, for this one, I apologize. Now it's this. Isn't it? Sorry about that. My bad.
It's centered at 2.5.
No, well, you can't do that. A pulse function's even. Remember? All right, for this one, I have 6. Now you're going to have to use the UN. Unfortunately, I can't use a pulse on this one because a pulse has to have an odd number. To use a pulse to represent these function has to have an odd number. I think that was a misprint. I think that's supposed to be. It's 1 from 0 to 6, I think, but it says 0 to 5. Does it give an answer for that one?
No.
All right, well, we're going to do it. For this particular one, then what you can do, I'm just going to tell you the easy way to do this one. You can do it with u of n. You could say it's what? U of n minus u of n minus 6, right? You can get the transform for u of n, right? And then you can get the transform for u of n minus 6 phase thing. That's more of a mess. Here's an easy way to do this one. Go right to the actual definition. Just say x of omega for this one would be equal to the summation because it's got an even number, not an odd number. Yes, sir?
Why do you have it where it's u of n minus 6?
Because then if you have u of n, it's 1 when n is 0, 1, 2, 3, 4, and so forth, right? Then you subtract u of n minus 6, so when it hits n equals 6, you get 1 minus 1. They're all zeros after that. This function could be defined as u of n minus u of n minus 6. Do you agree with that? How many see this right here? All right, you all agree. Because what? At 6, this is 1 and this is 1. 1 minus 1 is 0. What is it at 6? It's 0. Right? What is it at 7? It's 0. Well, at 7, u of 7 is 1. U of 7 minus 6 is u of 1 is 1, so I have 1 minus 1 is 0. All right, so that's it. That defines the function. Now, for this one, I'm getting back to it. I would just plop these values in. I know I've got a 1 there. From where? From 0 to 5, right? And then it's times the e to the j or e to the what? Minus j and omega, correct? And when you look at that, e to the minus j and omega, it's really like e to the minus j omega to the nth power. So it looks like a to the n, doesn't it, class? You all see it? Doesn't this really look like I have the summation? And I call my a here simply e to the minus j omega, right here. I'll get out of here. And now I can say that n equals 0. All the way to 5, I have my a right there to the n, or it's equal to a, which is e to the minus j omega, to the lower limit, or e to the, it's just going to be 1, minus e to the y, minus j, and then it would be upper limit plus 1, or j6 omega, right there, over 1 minus e to the minus j omega. Do you all see that right there? Y'all agree with that? This is the standard form that I showed you for the summations, where if you sum any a to the n, where n goes from q1 to q2, right? That's equal to a to the q1 minus a to the q2 plus 1 over 1 minus a. Do y'all remember that? Give me a show of hands, that one you have to know. You gotta know that one. I proved it, y'all remember, I proved it for you? It's a very, very, what, Josh?
Are we just dropping, like, yesterday when you gave us the transform for U of N, we had the summation, pi delta,
There's always gonna be that name.
so are we just ignoring?
No, we're not. This is the fundamental definition. Then there's, when you use the fundamental, you always have to add the 2 pi k to it. Because remember, this is gonna be over the visible region from minus pi to pi. Every time, you have to add that 2 pi k to take it out forever. Now, if you do the U of N one, it has it built in there, doesn't it? Look at U of N, transform U of N. What does it go to?
It goes to the 1 over 1 minus e to the j omega plus summation.
Of deltas, right?
Yeah.
That's because U of N has those deltas built into it, right? Oh, you're saying for this one, it didn't have the deltas, but the deltas will subtract out when you put them here.
But when we have the time shift, wouldn't the deltas be?
It's a phase, remember? What is it gonna be when it's at 0? It will subtract out, I promise you.
Okay,
I'll work with you on that, though.
all right.
I promise you it works. I'm just gonna tell you this one. Once you get this, then what he actually, he honed in on is, this repeats itself. This is true for omega is minus pi to pi, right? But you have to add the plus, everywhere there's omega, you have to add the plus or minus 2 pi k, and then put that sum out front from n equals minus infinity to infinity, because it repeats itself every 2 pi. Do you follow me on that? As a matter, if you track this answer, let me just tell you this. For this, actually, you won't have to with this one. It's self-repeating. If you just take this and add 2 pi here and here, it repeats itself. This is an automatic. This one's going to do this no matter, you don't even have to add all that other crap. It'll do it automatically for this one. Are you with me? But that 2 pi k, the delta stuff in the U of N is going to subtract out. And I know it will. I would do it this way. Anytime you have a finite number. All right? Got one? Is there another question?
That's the final answer.
This is an absolutely perfect, acceptable answer. Here's how they'll do it in the book. If there is an answer in the book, they'll factor out an e to the minus j6 here. So you'll get e to the minus j, or I'm sorry, not e to the minus j3 omega right here. And then you'll get e to the plus j3 omega minus e to the minus j3 omega. They'll replace it by 2j sine of 3 omega, follow me? And then downstairs, you're going to have a sine of omega over 2, and the 2 j's will cancel, you have a little phase term out front. Don't worry about that. They'll always do it that way. That way they can view the function. It's easier to visualize. That, I don't know what it looks like. I don't. Follow me on that? But that's the right answer. Yes.
So is that one where 3, then it would just be times 3, right?
What?
Is that one where 3, then everything
Yes,
would
yes,
just-
scale, absolutely, you're absolutely right. If there, she's saying, if this wasn't 1, 1, 1, 1, 1, suppose it was 3, 3, 3, 3, 3, all 3's here. You factor the 3 out. But then the 3 would appear here as a coefficient. Okay? All right, let me take care of a couple of things. Now, there's 2 things I want to tell you. I know this seems so abstract. Why are we wasting time? We're about to get to something where we're not going to be wasting time. We're going to get to a DTFT, which is an actual calculation that's doable and it's finite. It's very easy to do. Well, computers, they're very easy to do on computers. Let me be clear about that. But you use a lot of this information to gain insight, and also you can see trends and a lot of properties and stuff. So now I've got to tell you about 2 things. One is, a lot of times the way they define something, they might call X a vector. And what they'll do is they'll say X is something, we'll have this. It'll have some values, say 1, 3, 5, 7. Now they're not going to say what values of n those values represent. But all other values are going to be 0. And then they'll do something where they'll put a little bar under 1. That bar indicates n equals 0. Just write this down. That means it starts at -1, ends at what? 2, right? It goes from -1 to 2, right? It has 4 values. Do y'all agree with me? Class? Now, when you do these, it's best to just stick them right in the definition of the DTFT. You follow me on that? And just add them up. I'm going to do this one. I could say now my x of omega would be equal to the summation of x of n. N goes from -infinity to infinity. So this one starts at -1, right? And it goes to simply 2, doesn't it? And it's times e to the minus j n omega. And then you just write it out. That's all you do. So you start with n is -1, pardon me. When n is -1, I have 1 times this -1, so it's going to be e to the j omega. Do you follow me? Then when n is 0, right, that's 3. You follow me? Then when n is going to be 1, right, it's going to be plus 5 times e to the j minus j omega, right? And then when n is 2, it's going to be plus 7 times e to the minus j 2 omega. Are you with me? And that's it. That's all you do. You follow me? I literally I used the fundamental definition and I brute forced it. Now the reason I can't do some tricky little sum thing is because these values aren't all 1 or all a to the n or something like that. You follow me? They jump all over. So you do it this way. And I'm going to tell you for this one, just by looking, I can pull this out as a constant, 3. I see I have e to the plus j omega, e to the minus j omega times 5. I can factor out one of those e to the minus j omegas there. Then I can add minus 4j omega on the other side of it, so I can turn that into a sign. And then the other two, I basically have something that are exponential, complex exponentials. But the reason I'm going to tell you about this is this will become useful with the DFT. That's how you brute force one that's got a finite number of non-zero values. Are you with me? That are just jumping over erratically. Now, the thing I really wanted to get at was how to get the inverse DTFT. The DTF, or the forward transform, is basically there's 4 that you have to know. You have to know the delta function, right? Have to know a to the n, u of n, right? Have to know u of n. And then, well, I say the shift property, I stick it in there, I have delta of n minus some value, say k, what it goes to. But that's really a property. Then, when you have those, everything else you get with properties. You know, if you multiply by cosine of omega naught n, you get modulation. Sine omega naught n, modulation, right? If you have n times the function, what happens? This is all properties. You do what? J times the derivative with respect to omega of the x of omega, right? All the others you get by properties. And you know what? They're almost all identical to those. As a matter of fact, they are identical to the properties we know for the continuous time Fourier transform, which makes it great. Now, this is the inverse DTFT. Remember how we always did the inverse continuous time Fourier transform. We could, in some cases, use partial fraction expansion, but we like to limit that to Laplace, don't we? That's really a Laplace guy. So what we do, we use duality, don't we? Duality was the one property that made Fourier transforms so powerful that Laplace transforms don't have. Because if we knew x of t goes to x of omega, and the function we wanted to transform for, or the inverse transform, was like that x of omega only with omega bt, right? Then we could use duality. So I'm going to show you how powerful duality is for us with the actual discrete time Fourier transform. This is important, and it is very useful. First, I'm going to just say that, remember, x of t was equal to 1 over 2 pi, the integral from minus infinity to infinity of capital X of omega times e, and this is a plus j omega t d omega. That was the inverse transform, by definition, of the Fourier transform, the continuous time Fourier transform, right? Now, x of n And by the way, both of these are not called analysis, but synthesis. This will allow us to synthesize filter properties and see what the actual result we get when we hit the filter with an impulse function. This is going to be 1 over 2 pi, the integral from minus pi to pi of x of capital omega times e to the j n omega d omega. It's not a sum, it's an integration. Do you follow me? Now, this is the biggie. Pay attention to this. This is the one thing that you're going to get tested on all the time by me, and it's so valuable later on. In radar work, I make it a point to go through this stuff, just as a review with my radar class. Now, you'll notice these two. This has a capital omega, this has a small omega. Big deal, right? Instead of t, I have n, right? The integration is over small omega there, capital omega there. The real difference, and only difference, is in the limits. This starts from minus pi to pi, this starts from minus infinity to infinity. And here's the one thing. If you know a Fourier, suppose you're looking for the inverse transform of this one. I know I'm in a frequency domain and I have this. I have something that's minus pi over 2, pi over 2, height 1, and this is my x of omega, and I'm wondering what x of n is. And I don't know. So here's how you get it. If I knew the inverse transform of that, replacing capital omega by small omega, if I knew that inverse transform, now look, what happens here to that when I actually do this? Wouldn't the integration be, because it's 0 for what? Values of a small omega less than pi over 2, or capital omega less than pi over 2? Wouldn't this really start at somewhat less than pi over 2, right? In other words, it would be between minus pi and pi. Do you follow me? When the actual values, you're looking at an inverse transform of this, you'll notice this one's from minus pi to pi. So you go up here and you say, do you know the inverse transform of this function in the continuous time Fourier domain? So do I know the inverse transform, and what is this, by the way, by definition? Isn't that a pulse function of width pi of capital omega there? Isn't it, class? Well, go back down here and just do the whole thing, and suppose now this is the small omega domain. This is plus pi over 2. This is minus pi over 2. And this has a height of 1. This function is p pi of small omega, isn't it? Do I know what caused this? You do, don't you? How did we get it before? Come on. What do we know? What do you have to know to pass this class? Don't you have to know p tau of t goes to tau times the sinc of omega tau over 2? We all know that, don't we? That one. So use duality. Go here, you get what? Tau times the sinc, right? Not omega, but tau t over 2 goes to, guys, help me out. Don't forget the 2 pi. I keep beating on that one, but don't forget it. It's 2 pi times 1. Pulse with tau of equal. Technically minus omega, right? Right? But because it's an even function, it can be capital omega, or I mean positive omega. Now I can divide this by 2 pi, and I have this. So I know the relationship here, correct? You'll notice this only exists for tau. And if tau has a width that limits its existence between minus pi and pi or less, then you can simply take this transform. Please hear me. And I can replace small omega by capital omega. And then over here, you can replace t by n. N tau over 2. And here's what I'm really trying to say. If you're looking for the inverse transform of something, suppose I give you x of omega and you're looking for the inverse transform, think about this. Do you know the inverse transform of that function if it was into the small omega domain? You ask yourself that. Follow me? And if you do, then you can simply take that transform and replace t with n. And you've got the inverse transform of the discrete time Fourier transform. Are you with me? Now I did it for this one. So what does this one go to? Just look at it. This one right here. What would this be? Come on, guys.
Be 1/2.
Tau is what class?
Pi.
Pi, right? So when you look over there, it's pi over 2 pi or simply 1/2. Keep going.
Sync.
Sinc of
And pi over two.
n times tau is pi, right? Pi over 2, and voila, that's it. By the way, that is a non-causal response. That was a filter property. All right, so that filter can't be built, but it's for example. I could put a triangle function there. Do y'all see that? Can you get the inverse transform of a triangle function? Yes. As a matter of fact, there'll be more on that later, but that's a very powerful property. Now, I'm going to give you your quiz, and it's an easy one.